Today, we're going to continue our conversation about moment of inertia by learning how to calculate moments of inertia for composite shapes that are built up of simple shapes. So typically rectangles, triangles, maybe circles. So since the shapes are very simple, we are not going to integrate. And actually, this is how we typically calculate moment of inertia most of the time. In a lot of construction type applications, most beams are I-beams or box beams. They're usually made of simple shapes because they're inexpensive to fabricate. So our first step in solving these is going to be a table lookup. So let's say that our shape is built up of rectangles. Well, I want to look up in the table the moment of inertia for a rectangle. The table will typically indicate what is the x-axis, what is the y-axis, and what are the lengths of the sides of the rectangle. So the B is the horizontal side of the rectangle, and H over here is the vertical side of the rectangle. We'd have a rectangle whose area is B times H. And then what the table will tell us is what the moment of inertia about the x-axis is. If the x-axis goes through the middle of the rectangle or the centroid, that will be 1/12 BH cubed. The other moment of inertia you might need is the moment of inertia about the y-axis, going to be 1/12 HB cubed. Common mistake students make is using the wrong one of these or forgetting which one is B and which one is H. So here is how I get the right answer when I do this. This direction that is perpendicular to the axis is the direction that gets the cube on it. So if you're finding the moment of inertia about the x-axis, it's the H that's cubed. If you're finding the moment of inertia about the y-axis, it's the B that's cubed. The thing to point out is that the moment of inertia given in this format is for the moment of inertia about the centroidal x and y axis for the rectangle. In a minute, we're going to need that information when we go to combine multiple rectangles. What about a triangle? A height H, base B, there might be the x-axis, and your table would say that the moment of inertia about that x-axis through the centroid is 1/36 B H cubed. And again, the H is perpendicular to the X, and that's why that is the one that is cubed. The other really common shapes that we're going to use in class that are on your equation sheet for the final include a circle. Circle has an x-axis and a y-axis through the middle. And the moment of inertia about that x-axis is actually exactly the same as about the y-axis. It's equal to pi r to the 4th over 4. Might not be surprising that the radius of the circle shows up in there. And the last one is, what if you had a quarter circle? Instead of giving it through the centroid, the table gives us the moment of inertia about an x-axis or a y-axis at the edge of the quarter circle. And that happens to be exactly pi r to the 4th over 16. So if you have any of these shapes in your composite shape, your first step is to look up and find the moment of inertia. There's our first step. Next step is we're going to use what's called the parallel axis theorem. Now, I've introduced this before in class, but here's a reminder of what it is. If I want to find the moment of inertia about any x-axis in the world, that is equal to the moment of inertia about the centroidal x-axis, we call that I bar x prime, plus the area of the shape that I'm using the parallel axis theorem applied to, times the y distance between those two axes squared. Or let's do it also for the y-axis, because we're going to do moments of inertia about both axes today. The moment of inertia about any old y-axis will be the moment of inertia about the centroidal y-axis plus the area times the x distance between those two axes squared. And what we do with this is we're going to move all of the moments of inertia to the same axis. Let me draw a quick picture to show you what I mean by that. So let's say I had a rectangle attached to another rectangle attached to yet another rectangle. And I needed to find the moment of inertia of all of those about some axis. Well, when I do the table lookup, I would be able to find the moment of inertia of this top rectangle about an axis through its centroid. Call that the x1 axis. And then I would look up for my next rectangle and I would get the moment of inertia about its centroidal x-axis, call it the x2 axis. And then finally, I've got my third shape. It's got a centroid at a totally different location. So I would be finding the moment of inertia about that x3 axis. And all of those happen to be the centroidal axes of the individual shape. So if I wanted to find the moment of inertia when I'm done about an axis all the way down here, the x-axis, right? What I'm going to be doing then is I need to apply the parallel axis theorem first to this rectangle. And I would use, for that purple axis, I would use this would be my dy, which I will square. Then for the blue axis, this would be my dy, distance in the y direction. And finally, this right here would be my d with a subscript y. So for each of those areas, I'm going to grab the 1/12 BH cubed and I'm going to calculate it for this area, then add to it this area plus this distance squared that gets me from the centroidal axis, I called it the x1 axis, all the way down to the overall global x-axis where somebody asked for the moment of inertia. And then for this next shape over, I'd use its 1/12 BH cubed, and then I need to use its area times its distance between its centroidal axis x2 and the overall axis x. And then finally, this area, I would need to find the moment of inertia of this shape about its own centroid, and then I'm going to take the area times the distance between the two axes squared. And once I've done that, then my third step, when I'm done with that, is that the total moment of inertia of the x-axis is the sum of all of the moments of inertia about that same axis. And the point is to add them up. These must all be the same axis. So you may need to apply the parallel axis theorem to multiple shapes to eventually get the moment of inertia of each of your separate shapes all about the same axis, and only then can you finally add them all up. So let's do this with an example. The example I have is these three rectangular shapes have been glued or nailed together. They're stuck together somehow. So the shape we're interested in is actually this shape right here, this area. The board in the middle is 12 by 2, and then the board on the side is 2 inches wide, and it looks like it's 6 inches tall, and this one is another 2 by 6. And the problem asks us we actually need to do two things for this. First of all, we're supposed to find where is the centroid, and they ask us to find it relative to the axis at the top. We're going to call that axis at the top the x-axis. So once we find the centroid location, we're going to find both the moment of inertia about that x-axis at the top, and once we know the centroid location, we now know where the x prime axis is. It's through the centroid, and so we're going to find the moment of inertia of the whole shape about the centroidal axis. So we're going to review centroids first and then do moments of inertia. To find the centroid, the equation for y bar is the sum of all the little y tildes times each area divided by the total area. So you can put this in a table if you like. I think it's just a little bit faster to write it with just one giant fraction. So let me color code each of my shapes. We'll make this one kind of a pinkish purple color. We'll make this one on top a green rectangle, and then maybe make the one on the right kind of orange. That blue doesn't really look like orange. It'll work. So that first rectangle, we need to find y tilde is the centroid location of the specific rectangle measured relative to your reference or x-axis. So you need to start at the x-axis and go down halfway. So it'll be 3 inches down. So we've got 3 inches, and the area is just a rectangle. So it'll be 2 inches times 6 inches. Then in the bottom of the fraction, we do just the area, 2 inches times 6 inches. Next, we'll do the green one. The green one is 2 inches tall. So its centroid is going to be halfway down, 1 inch down. So the y tilde is 1 inch. And the area it is 12 inches wide and 2 inches tall. So on the bottom, we'll put 12 inches times 2 inches. And then we have one more shape. It is another 6 inch tall rectangle. So the centroid will be 3 inches down. So we'll put in 3 inches for the centroid of that rectangle. And the area is 2 inches times 6 inches. Put the area only on the bottom, 2 inches times 6 inches. And let's multiply it all out. We get that the centroid location, y bar, actually comes out to be exactly 2 inches in this case. And you remember what I told you guys when we learned centroids? Your centroids of the different individual shapes are located 3 inches down, 3 inches down, and 1 inch down, right? 3, 3, and 1. So the actual centroid should be somewhere in between 3 and 1. 2 is definitely in between 3 and 1. So I feel pretty confident that that's the right answer. Now, later on, you'll notice parallel axis theorem had the area in it. And right here in this calculation, I actually calculated the area along the way. So I find it really helpful to just write that down. The total area of the shape has to be square inches. Calculate it once and then use it again later in the problem. On to the new fun stuff. We need to do moment of inertia. We've got 3 shapes to find the moment of inertia of. I like to do the x-axis first. And the reason I like to do the x-axis first is that we just found the distances from the x-axis to the centroid of each shape. That's our dy that we're going to square in just a minute. So since I already just found these, it's really handy to just use them again. Moment of inertia of a rectangle is 1/12 bh cubed. B is the side parallel to the axis. So for that purple rectangle, it'll be 2 inches. And then h is the side perpendicular to the axis. So that's going to be 6 inches, which will get cubed. So there's the moment of inertia of about the centroid of this shape, that axis down there. So to move it up to the x-axis, I need to add to it its area, 2 inches times 6 inches, and the distance squared. We got the purple one. Let's do the green one. Plus, we'll still use a 1/12 because it's still a rectangle. The base is the side parallel to the axis. That'll be 12 inches. And the height is 2 inches, which gets cubed. And then we add to it the area, 12 inches times 2 inches times the distance between which 2 axes? The centroid of the shape we're finding the moment of inertia of, which is the green rectangle, and the x-axis. So it's a 1-inch distance, which gets squared. Remember, the 3-inch matches the 3 inches we used when we found the centroid, and the 1 inch got the centroid. Next, orange rectangle is going to be 1/12. The base is going to be the 2 inches that's parallel to the x-axis. The height is the 6 inches, which is perpendicular to the axis, so it gets cubed. We add to it the area, 2 by 6. And again, it's going to be a 3 inches, which gets squared. The 3 inches is the same thing we used here. It's the distance between the centroid of the 6-inch tall rectangle and the x-axis. Okay, we multiply that all out and we get our answer. And if you should double check, every single term here has inches to the 4th, so your answer should be inches to the 4th. What about Ix prime? There's actually 2 ways to get the moment of inertia about the x prime axis. I'm going to show you both of them. The first way is to repeat what we just did, and we can quite literally copy and paste the moments of inertia about the individual centroidal axes, because those don't change. All right, so same moment of inertia about the centroidal axis of each shape. What is different? Well, now, instead of transferring it from the centroid of that shape to the top axis, we're going from the centroid of that shape to the x prime axis. So the distances will be different. The area is still the same. So that first purple rectangle, right, the reminder is our overall moment of inertia was 1/12 bh cubed for the purple rectangle. Now I need to add to it its area, 2 inches times 6 inches. And then the distance now is the centroid of the rectangle itself is 3 inches down from the top. And the overall centroid y bar is the difference between the two. 3 inches minus 2 inches, and then we square that quantity. What we're doing is we're taking the centroid location of the actual shape, which is 3 inches from the top, and subtracting from it the centroid location of the whole shape, which is where that x prime axis is located. The difference of those two is 1 inch. It gets squared. Same thing for the green rectangle in the middle. We end up with area, 12 times 2. And then I need the difference in the centroid of the whole shape and the centroid of my own shape. So the green rectangle is 1 inch below the top. The whole shape centroid is 2 inches from the top. You subtract them and you square it. We're going to get minus 1 inch. We square it, it becomes plus 1 inch squared. And then let's do the orange rectangle. Same thing, the shape, the area is 2 by 6. And then I want to find the distance between the centroid of the whole shape and the centroid of my rectangle. And the center of my rectangle was 3 inches down, centroid of the whole shape was 2 inches down. Subtract them. 3 inches minus 2 inches, quantity squared. And we get a number. It comes out to be 128 inches to the 4th. Really key point. The moment of inertia about the centroidal axis for a shape, composite shape or otherwise, will always be the smallest moment of inertia you get. So see how 128 is smaller than 320? That makes sense. As you get farther and farther away from your centroidal axis, we evaluated it for x. We could have come up here 5 inches higher and evaluated it again. the farther you get from your centroid, the bigger your moment of inertia becomes. It's always smallest at the centroid, and it absolutely always has to be positive. You noticed everything we added up in here was positive. The only thing that was negative was the 1 inch minus 2 inches was negative, but then it gets squared. So moments of inertia have to be positive, and the moment of inertia about the centroid must always be smaller than the moment of inertia about any other parallel axis to it. But I want to show you a shortcut to get this answer. We could actually instead apply the parallel axis theorem to the whole shape. So every one of these colorful combinations is using the parallel axis theorem. For the purple rectangle, I knew the centroidal moment of inertia. I add AD squared, and I get, for the purple rectangle, its moment of inertia about this x-axis. Repeat for the green rectangle. Repeat for the orange rectangle. So we just use the parallel axis theorem applied to each individual shape. We can also apply it to the whole shape. Still the same equation, Ix is equal to I bar x prime for the whole shape plus the area of the whole shape times the distance squared. Now, the way we would use this is if we've already solved for the moment of inertia about the x-axis, we got 320. Let's plug it in. 320 inches to the fourth equals, now pretend we didn't just calculate I bar x prime, we want to find it. Let's leave it as our unknown. Now add in the area, not of an individual rectangle, but of the whole shape. Did you notice I calculated it before and I saved it? It's 48 square inches. And now what I need to do is find the distance between the two axes. Which two axes? The x-axis that I found my 320 inches to the fourth about, and my x prime axis. Oh, that's just y bar. That's just 2 inches. So times 2 inches squared. Solving. So you're going to take this on the right and subtract it from that on the left. And what you get equals 128 inches to the fourth. Same answer, way less math. Let's do this again. Let's try it for another problem. So this one is a T-beam, a little bit less math because we can break this up into just 2 rectangles. And it does look like I lost one of my dimensions. This should be 50 millimeters. So I've got 2 shapes. I'm going to break them up. We got a purple rectangle, and let's make this one kind of green. Purple and green rectangles, that's our shape. And it wants us to first find y bar, and they gave us the x-axis down here at the bottom, so we're going to be measuring up to get y bar. Then it asks us to find the moment of inertia about the x prime axis, but I want to do more. I want to find it also about the regular x-axis, as well as the moment of inertia about the y-axis, because I think it's good practice to see all the different moments of inertia that you could get. First up, we got to find that centroid. So y bar is the sum of the y tildes times each area divided by the sum of the areas. We only have 2 shapes. So that first shape is the purple shape. We need to find its centroid. Well, the rectangle is 50 tall, so the centroid would be 25 from the top. We don't want it from the top, we want it from the x-axis down here. So I got to come up 250 plus another 25. That should be 275 millimeters. And then the area will be 50 times, it looks like it's 300 millimeters wide. So on the bottom of my fraction, I put just the area part, 50 times 300. Now I'll do the green rectangle. The height is 250 millimeters. So the centroid will be 125 up from the bottom. The area of that one, it looks like it's 50 millimeters wide and 250 millimeters tall. And in the denominator, you just put the area, 50 times 250. We multiply that all out and we get a number for y bar. And it comes out to be 207 millimeters. Does that make sense? Does it pass the reasonable test? Well, my 2 centroid locations were at 125 and 275, and it is in between them. So yes, passes the does it make sense test. We also get that total area from the bottom of the fraction is 27,500 millimeters squared. I really like finding Ix right after finding the centroid because we already know the distances to use. So to do moment of inertia about the x-axis, the table lookup tells me for a rectangle, I'm going to use 1/12. The base will be 300 millimeters. I'm not going to write all the millimeters down just to make it a little bit more compact. And then the height would be 50 millimeters, which gets cubed. And the reason the 50 is cubed is because it's perpendicular to my x-axis. Now that gives me the moment of inertia about this x-axis through the centroid of my little purple rectangle. But get the moment of inertia all the way down at the x-axis, I got to add to it area, 300 times 50 times the distance squared. And the distance is sitting right there. It's the 275 that gets squared. Why is it 275? Because we got to go from this centroid location, which is 275 above this x-axis. Let's do the green rectangle next. So 1/12, the base this time is 50, and the height is 250, which gets cubed. That's the moment of inertia about the centroid of the green rectangle. To move down to the x-axis, now I need to add AD squared. So the area is 50 times 250, and then the distance will be just 125, which gets squared. 125 is sitting right here in your centroid equation, but it's also just the distance from the centroid of the rectangle to the bottom. And we run that all through our calculator, and we get that the moment of inertia is 1398 times 10 to the 6th millimeters to the 4th. Now I want to talk for just a minute about units. In SI units, you're either going to have a giant number of millimeters to the 4th or a very tiny number of meters to the 4th. We often, I know you could write this as 1.4 times 10 to the 9th millimeters to the 4th, but we usually like to write this times 10 to the 6th. And the reason for that is if I wanted to convert this from millimeters to the 4th into meters to the 4th, you would need to divide it by 1,000 4 times because you got millimeters to the 4th, or multiply it by 10 to the minus 12th. So what this is going to be equal to is 1398 times 10 to the minus 6th meters to the 4th. And we tend to find it really convenient if we just always write it as 10 to the 6th and 10 to the minus 6th. Makes it quite easy to convert back and forth between millimeters to the 4th and meters to the 4th. Again, it would be more convenient maybe to write this as 1.4 times 10 to the 9th, and this one is 1.4 times 10 to the minus 3rd. Also correct. The answers in the textbook are definitely always going to be times 10 to the 6th and 10 to the minus 6th. Okay, what do we need to do next? We've got Ix. We need to find I bar x prime. And should we do it both ways again so that you believe me that it works both ways? Let's do it the fast way this time. So using the parallel axis whole thing, we know that Ix that we just found, that's our 1398 times 10 to the 6th millimeters to the 4th, is equal to I bar x prime plus the whole area times the distance in the y direction squared. Well, we don't know I bar x prime, but we do know the area, 27,500 millimeters squared, 207 millimeters, and square it. So I need to do this multiplication, subtract it to the other side, and I will get that I bar x prime, the fast way, is 220 times 10 to the 6th millimeters to the 4th. Let's do it the slow way, just for practice. The other way to do that would be I bar x prime is equal to, go and do it individual rectangle by individual rectangle. We'll have the 1/12 times 300 times 50 cubed, just like we had before. Same area, 300 times 50. But now we don't want the distance between the centroid of this shape and the x-axis. We want the distance between the centroid of this shape and the x prime axis. We want that distance. Well, the easy way to get it is actually to go all the way down to x. I know that distance is 275. And then the centroid to x is 207. I just need to subtract those two. So I'm going to write it down as 275 minus 207. And that difference gets squared. And then let's do the green rectangle. We'll end up with the same thing, 1/12, 50, and the 250 gets cubed. The area is 50 times 250, and then the distance is going to be not the 125 millimeters that went from the centroid of the green rectangle to the x, but I want the distance between the centroid and that 125. So if the centroid is 207 up and the center of the green rectangle 125 up, I can just subtract those two. You can subtract them any order you want. You can take the 125 minus 207, it'll be negative, but then when you square it, the negative goes away. And if you run through all of that math, it's more math, you should get 220 times 10 to the 6th millimeters to the 4th. Okay, we have one more thing to do. Moment of inertia about the y-axis. If I do moment of inertia about the y-axis, it's going to be the same as x, except I have to basically just flip b and h. because with the y-axis, the side that's perpendicular for that purple rectangle is 300 millimeters. So that's the one that gets cubed. So we're going to have for the purple rectangle 1/12, instead of 300 times 50 cubed, it's 50 times 300 cubed. That's really all you have to do to go from x to y, is just switch which one you're cubing. And then what about AD squared? Well, the area is 300 times 50, but what is the distance? I want to find the distance between the y-axis, where I want the combined moment of inertia, and the centroidal axis. Did you notice the centroid of this rectangle right here is right on the y-axis? So you could put the area in there if you want to make sure you haven't forgotten it. 50 times 300 is the area, but the distance is 0 because the centroidal axis of the little purple rectangle is right on top of the y-axis. So that whole term will be 0. And now let's do the other rectangle. Is 1/12. We got to flip. Instead of 50 times 250 cubed, it's going to be 250 times 50 cubed. Again, the area is 250 times 50. But the distance, did you notice this is exactly centered on the y-axis? So the centroidal axis of the green rectangle is the y-axis. So the distance, again, is 0. So you could just totally leave these terms out. When all of the axes line up, you don't need to use the parallel axis theorem. You can just add them up directly. And so this comes out to be 115 times 10 to the 6th millimeters to the 4th. And that happens to also be I bar y prime, because the y-axis already goes right through the centroid. So much easier when all of the axes line up. All right, one more problem. When we did this live in class, we did this as a top hat problem, and we did step by step. I stopped and I let everybody try to calculate the steps. So I think the hard part of these is doing them on your own, not watching me do them. So strongly suggest that you pause the video after each step and see if you could actually calculate it. So we are going to need to break this shape up into rectangles. And I decided to break it up into one rectangle that was 3 by 1 right here on the end. The other side, I broke it up into a rectangle that was 1 by 8. And so then the rectangle in the middle is actually not a 10-inch long rectangle. It's only an 8-inch long rectangle. This is not the only way to break it up, but this is how I did it. I broke it up into those 3 shapes. We want to find out how far over in the x direction do we have to go to get to the y prime axis, and then find IY and the moment of inertia about that centroidal y prime axis. First, you find the area of the shape. So pause the video, try to find the area. The area should be 3 times 1 plus, for the blue one, 8 times 1 plus for the pink one, also 8 times 1. Should come out to be 19 square inches. And it's surprising actually how many students in class don't get that number right. And I think the reason is that you're not drawing out the actual shape. And so many students would put this 10 inches in for the area of this bottom blue rectangle. But you have to decide, are you going to cut it like this, make it a 10 by 1 rectangle? Because then this becomes a 2 by 1 and this becomes a 7 by 1. So I strongly recommend drawing out your actual shapes you're going to use. Color code them if you like colors, because it helps you get the answers right. So next step is find the actual centroid location. Is this the sum of the tildes times area over the sum of the area, which is our 19 squared inches that we already know. So if you want to pause the video, do your own calculations, then turn it back on and see if you got it right. The way this will work for my green rectangle, on the top of the fraction, I'm going to have distance that I have to go over from the y-axis to get to the centroid. So I'm going to have a 0.5 times 3 times 1. I already know the area, but in the bottom you would have a 3 times 1 if you did this in one step. Plus, for the blue rectangle, the centroid location. Well, the whole thing, the way I did it, is 8 inches wide. So the centroid is 4 inches over, but relative to the y-axis, I got to add 1 more. So you got to go 5 inches to get from the y-axis to the middle of the blue rectangle. So we've got 5 times 8 times 1 for the blue rectangle. In the bottom, just get the 8 times 1. And finally, that pink rectangle. Well, it's 1 inch wide, so its centroid is a 1/2 inch over. But first, you had to go 9 inches before you got to the pink rectangle, right? 1 plus 8 is 9 plus a 1/2 more. So this one would be 9.5 times 1 times 8, or 8 times 1. Okay, the bottom of that fraction is 19 square inches. We already found that. The x coordinate of the centroid comes out to be 6.18 inches. We got our centroid practice in for the day again. Next, we need to find the moment of inertia about either the y or the y prime axis. I like to do IY. And we first need to figure out the moment of inertia of this first little green rectangle about its own centroidal y-axis. And then we'll add AD squared to it to move it back here. So this step is going to be 1/12. Now, my question for you is, what gets cubed, the 1 or the 3? And it always decide perpendicular to the axis that gets cubed. So since the axis is the y-axis, it's the 1 that gets cubed. So 1/12 times 3 times 1 cubed. We add the area, 3 times 1, and then the distance is the distance between the y-axis and the centroid, 1/2 inch, that gets squared. Then we add the blue area. 1/12 in this case is going to be 1, and it's the 8 that's going to get cubed, because the 8 is the length that is perpendicular to my y-axis, so that gets cubed. Then we add to it the area, 1 times 8, and then the distance from the centroid of the blue shape all the way back to the y-axis, which we already figured out was 5 inches. So 5 squared. Finally, the pink or purple rectangle, we're going to have 1/12. The base in this case is 8, and the height is 1. By base, I mean side parallel to the y-axis. So the bases would be 3, 1, and 8. Those do not get cubed. And the height, if you thought of turning your paper sideways, is the perpendicular distance, 1, 8, and 1. So the 1, 8, and 1 get cubed. But again, we need to add area, 8 times 1. And then the distance is that 9.5 inches, which needs to get squared. This comes out to be 966 inches to the 4th. That's the moment of inertia about this y-axis all the way over here. Now we want to find the moment of inertia about the y prime axis. Let's do it the fast way. To do that, we remember that the parallel axis theorem says IY is the centroidal moment of inertia, I bar y prime, plus the total area times the distance in the x direction squared. I know IY is 966. I just found it. Now I need to find I bar y prime on the right side. Add to that the total area, that was that 19 square inches we found at the beginning, and then the distance in the x direction between the two axes, oh, that's just x bar. We also found that already. So this gets multiplied by 6.18 inches, which gets squared. So rearranging and solving, I bar y prime is 240 inches to the 4th. And that is the end of this set of notes on finding moments of inertia of composite shapes. In your homework, you may have some other shapes like triangles or circles or whatever. And the process is exactly the same. All you're going to do is instead of 1/12 BH cubed, you'll have a different formula. It might be 1/36 BH cubed for a triangle, or pi r to the 4th over 4 for a circle. So you just look up for whatever shape it is. What is that moment of inertia? Look for the simplest thing possible. Let me give you an example. If I have a shape that is a square with a square hole in the middle, well, the centroid is in the middle. So there is my x and my y axis. There are several ways to solve this problem, okay? The hard way is to take that box and break it up into 4 rectangles. It's not that 4 rectangles are hard, but the problem that you're going to have is, say you're finding the moment about the x-axis, the centroids are at 4 different locations. So you're going to have to use 4 shapes plus the parallel axis theorem. There's an easy way to do this one. Easy way is do moment of inertia of big rectangle minus moment of inertia of little rectangle. It is that fast, because guess what? The centroid location of the big square and the little square matches the centroid location of the overall shape. So all you need to do is 1/12 BH cubed for that shape minus 1/12 BH cubed for that shape. In order for this to work, the shape has to be symmetric so that the centroid of the big shape and the little shape and the x-axis are all at the exact same location. If it's not symmetric at all, you have to do it the hard way and break it out into simple shapes and use parallel axis theorem. But if it is perfectly symmetric, like a perfect box beam or a perfect circle with a hole, the moment of inertia about the x-axis here would be pi outer radius to the 4th over 4 minus pi inner radius to the 4th over 4. Just the moment of inertia of the outer circle minus the moment of inertia of the inner circle. So one more handy trick and tip: if you do have a shape that's totally symmetric, you can save yourself some time by subtracting big shape minus little shape.